Welcome, everyone. My name is Valentina Rozanova from TRC and New Jersey's Clean Energy Program. Thank you all for registering and being here on what is a very summer-like day on the East Coast, if you're with us on the East Coast. So I'm sure many others are itching to take a little time off and enjoy the weather, but hopefully we can get through the presentation and get you back to your day fairly quickly. Today we have two presenters. We have John Sousa, who's our outreach account manager here at TRC and New Jersey's Clean Energy Program. He's going to go over a new construction program overview, which we like to do this at the beginning of every webinar that we've been doing. Some of you may have heard some of this already if you've joined us for one of the previous 3 webinars, but he'll just briefly give an overview of our new construction offerings and also provide updates on a couple of things, particularly the program transition that has been ongoing that some of you may also be somewhat aware of. And then we'll switch over to Christina LaPearl. She's with Cartman Consulting, and she's going to go through the core presentation that we have today regarding integrated design and ASHRAE bEQ compliance path. If you have questions, so everyone joined on mute as default. So I would ask that as we go through the presentation, if you have a question come up, that you place it into your chat box. If the question might be beneficial for the group, you can post it to everyone. If you'd rather not do that, you can just post it to myself, the host. And then when we get to a stopping point, we'll address whatever questions come up in the chat. If we're at a stopping point and you'd rather ask your question live, just press the raise hand button on the bottom of your reaction screen. And I will then unmute you, and that will allow you to unmute and speak to us. That's all that I wanted to cover before we get started. So I'm gonna stop sharing and I'll hand it off to John.
Thanks, Val. Good afternoon, everyone. My name is John Sousa, and on behalf of New Jersey's Clean Energy Program, I want to welcome you all today to the final session of the Pay for Performance training webinar series. So I represent New Jersey's Clean Energy Program as a commercial and industrial outreach account manager, and I'm happy to be part of a professional, dedicated, and diverse team who help New Jersey ratepayers take advantage of the generous incentives offered by the Clean Energy Program. Today, I will present a high-level overview of New Jersey's Clean Energy Program's portfolio of incentive programs and introduce those programs that can best be utilized for new construction projects. So for a bit of background, the Clean Energy Program is administered by the New Jersey Board of Public Utilities, and funding for our energy efficiency rebate and incentive programs are provided through the societal benefits charge that ratepayers will find on their investor-owned utility bill. Along with helping residents and businesses save money, these incentive programs have an obvious positive impact on the environment, lowering emissions and helping the state meet its goal of 100% clean energy by 2050, as published in New Jersey's Energy Master Plan. So our energy conservation and efficiency programs obviously help limit the amount of energy consumed, resulting in additional cost savings, and help build a more sustainable energy future for New Jersey. For added energy resiliency, we also offer other programs related to distributed energy, such as combined heat and power and fuel cell technologies. All of our energy saving and efficiency programs act as the logical first step, allowing for better integration of renewable energy technologies like wind and solar. The Clean Energy Act of 2018 set the stage for the creation of specific energy goals as outlined in New Jersey's Energy Master Plan, and provides guidance for the Clean Energy Program. New Jersey's Energy Master Plan serves as a roadmap to achieve New Jersey's ambitious energy goals, and this document is closely monitored by all industries in New Jersey, helping to identify how they can help support our ambitious energy targets. And these goals include 100% clean energy by 2050, a large reduction in carbon emissions, and to ultimately promote a stronger and fairer New Jersey. And this last element addresses the need for economic, social, and environmental equity through energy conservation and resiliency. So now I'll describe some of our recent highlights and our results in a much more tangible way. And these next couple slides reflect the performance of our program for the last fiscal year And we thank all of you for your contribution, as this is a direct result of the work and efforts of our participating contractors. In fiscal year 20, we processed over 140,000 applications, resulting in nearly $140 million in paid incentives. These energy savings were delivered and realized through efficiencies in electricity, gas, and oil consumption, as well as other forms of energy generation. Having a background in environmental science and sustainability, I do enjoy this slide because it shows the tangible benefits of our initiatives. The amount of CO2 emissions saved from our program during the last fiscal year equate to over 159,000 cars removed from our roadways and over 12 million trees planted. The big takeaway here is that the amount of greenhouse gas eliminated has an obvious impact in furthering a more sustainable energy future for New Jersey. And how we achieve these results is through a wide range of programs offered within our portfolio. As you can see, we have 5 different buckets of energy-related programs, in addition to our suite of commercial, industrial, and residential incentive programs. We have other programs related to renewable energy and specialized energy efficiency programs and grants for new initiatives and research and planning. As some of you may already know, the structure of the programs will be impacted by New Jersey's upcoming energy efficiency transition. And this shift in energy efficiency governance was mandated by the governor in 2018 through the Clean Energy Act that requires utility companies to reduce their energy demand. This transition will ultimately serve as a benefit to end users and customers as the availability of on-bill financing will increase. So once the transition does begin, a portion of both the C&I and residential energy efficiency subsets of programs are transitioning to be managed by the investor-owned utility companies, as mandated, as I said, by the 2018 Clean Energy Act signed by the governor. And as you can see here, both C&I and residential existing building programs and efficient product programs are transitioning to the management of the utility, while the rest of the programs, including new construction, stay with the Clean Energy Program. The act requires that the utility companies reduce their customers' use of natural gas and electricity, obviously by set percentages over the next 5 years. Here's a good timeline. And as you can see, PSE&G has already launched their appliance recycling program at the end of last month. And in just a couple of days here on the 24th, we will see the launch of their commercial and industrial prescriptive and custom existing building programs. The other utilities are due to launch come July 1st. And as a reminder, the programs that I'm presenting today and we're going to be talking about are still accepting applications for customers until the launch of the utility programs. And obviously those that are new construction applicable, those will remain with the Clean Energy Program. But we will still see through all applications of all our programs in the pipeline for qualifying projects. And as I said, the theme today is obviously new construction. So it's good that we're talking about transition in the sense that these programs will be staying. But I will take some time now to go over the new construction programs before handing it off to Christine. As a outreach account manager, my job is partially to perform an initial triage with potential new construction end users. And this is where we determine initial eligibility based on the utility bills and the size of the building or new construction project. And this is especially important for pay for performance because of the requirement of 50,000 square feet or more or of conditioned space. Whereas Smart Start or our single measure review program, I guess is our catch-all program for single energy consuming pieces of equipment like HVAC units or lighting. As a part of our initial triage, we also determine eligibility for our residential programs, especially in the case of multifamily new construction projects. The projects may be referred to the residential team if they are pursuing Energy Star new construction, or P4P if the building meets the size qualifier. I'm sure most of you are familiar with the Pay for Performance program, but as a reminder, in order for a new construction project to qualify, it must have 50,000 square feet or more of planned and conditioned space. Additionally, substantial renovations will also be eligible for Pay for Performance for change of use, reconstruction of a vacant structure, or whereby the nature of the construction project, the building or portion of building will be out of service for at least 30 days. We inform all potential users that because of the approval and verification process, Pay for Performance projects may take up to 2 to 3 years. However, the incentive values are significant as they can be up to 70 to 80% of the total project cost. So we always like to highlight a success story, and here's an example of a new construction multifamily high-rise project located in Jersey City. They use the Pay for Performance program to realize energy savings of more than 1 megawatt hour of electricity and save nearly $200,000 in electricity per year. These energy efficiency measures resulted in a relatively short payback period for this project of about 1.5 years. So moving to our single measure rebate program, Smart Start is used to cover energy efficiency equipment for upgrades for commercial, educational, governmental, and agricultural customers engaged in new construction events. Smart Start eligible components include lighting systems, HVAC systems, and other energy using equipment. And it's important to note that new construction projects do not qualify for enhanced incentives under this program or any new construction program for that matter. However, we do offer technical support and help in navigating the application process. So there are 2 tracks for the Smart Start program. The prescriptive track includes a list of certified energy efficient equipment from the Energy Star or DLC websites. And this covers anything from lighting, electrical chillers, variable frequency drives, gas heating to food service equipment. And this list is quite extensive and it's on our website. All the eligible equipment is listed there. Alternatively, you can use the custom route for emerging technologies that are not covered under the prescriptive measures, but can still show cost-effective energy efficiency improvements. Although pre and post inspections are required for custom measures and they must meet code for retrofit projects. Complementary single measure rebates for multifamily new construction are also available within the residential suite of new construction programs. And within the residential portfolio, the residential new construction program is designed to provide builders and homeowners with a range of participation options. There are 3 different levels of energy efficiency options for new homes, as well as a multifamily high-rise program, which requires 15% increased energy savings above code. Benefits of our residential new construction program include better wall-to-wall comfort and ultimately durability, high performance heating and cooling, and a tighter overall building envelope. Additionally, single measure appliance rebates can be obtained through our residential new construction program. So one last bit of recap about transition, just to leave you with. After July 1st, we hope to see the launch of all the existing building programs and the utilities. And New Jersey's Clean Energy Program will continue to serve all new construction clients, as well as perform local government energy audits, provide alternative funding through our Energy Savings Improvement Program, and administer the combined heat and power and fuel cell programs. We suggest that you check out our website regularly to review the updated information, as the frequently asked questions and responses will also be updated as the answers become known. We encourage you to use our programs until the utility programs are available, and we will continue to use the website to provide the updated information. So thanks everyone for your time this afternoon. And as mentioned before, I'm here to answer any of your questions you may have about these or any of the programs contained within our portfolio. And I'm also happy to give separate presentations to your individual organizations or anyone with an interest in learning more about what the Clean Energy Program has to offer. So please take down my information and reach out. I'll now hand it over to Christina for her portion of today's presentation. I see here a question about the total cost of the project. Yeah, that it wasn't the entire cost of the building project in itself. It was the energy efficiency upgrades. Right.
Right, the incremental cost. And I'm sure we have total cost somewhere as well, but obviously it's going to be in the multi-millions dollar.
I would imagine.
So sorry, Christina, your floor is yours.
Thank you, Val. Thanks, John. Good afternoon, everyone. Thanks for joining today. Our presentation this afternoon is going to be on integrated design, which essentially includes a discussion of early design modeling and also how it relates to the pre-design bonus that the P4P new construction program offers. And then the ASHRAE bEQ path is another path, and I'll talk about that more. that is not as commonly used as Appendix G. So we just wanted to provide a few more details on that path. As Val said, my name is Christina LaPearl. I'm part of the review and tech support team for the program. I do both energy modeling and reviews myself, and I'm a recent member of the ASHRAE Standard 209 committee, which is relevant to this discussion, and we'll get to that actually in a few slides. So the agenda for today will start with a brief introduction. Then we'll get into discussing energy modeling, so that early design energy modeling from the concept phase of design to construction documents. So we'll really focus on that period. Then we'll talk about some high performance case studies so that you can get a sense of the type of measures that are included in designs where really high performance has been achieved. This is primarily because as codes become more and more stringent, we're looking for ways to make our designs more and more efficient. Then we'll talk about the ASHRAE bEQ path for 20 minutes, and then we'll stop for some questions. And I might stop about midway through before the case studies if there are any questions in the chat. Okay, so the objectives for today are to understand the benefits of energy modeling early in the design process, and also the requirements for the program in order to achieve that pre-design bonus. I want to make sure everyone is aware that there are requirements. So you can't just do a model at schematic design stage and think you're going to get the pre-design bonus. You have to make sure that you're checking all the boxes in the partner guidelines. I'm going to just want you to be able to describe the progression of energy modeling as you move from those very early concept phase stages to the construction document stage. And when we talk about those case studies, we want you to be able to walk away and identify the common design opportunities and features in high performance buildings. And lastly, to understand the concept and the benefits of trying out the bEQ path for demonstrating performance for the program. Okay, so for the P4P new construction program, there are two paths to demonstrating performance. There's the ASHRAE bEQ as designed path and the ASHRAE 90.1 2016 Appendix G path. So regardless of which path you select for demonstrating performance with the program, both paths will equally benefit from early design modeling. So briefly, I just want to touch on the basic concepts of both of these paths. With the ASHRAE Appendix G path, you have two models. You have the proposed design model, which is essentially your as designed building. And then you have a baseline design model, which is developed using the rules in Appendix G. There are some commonalities across the model, like the weather file used, the simulation tool used, and the utility rates. And then we compare the performance of the proposed design model to the baseline to figure out which incentive tier you fall in for the program. And I've listed those tiers on the slide. So if you achieve 10% above code, which is the baseline, and you're a commercial building that's not multifamily, you're in tier 3 and you qualify for the highest incentive. So for the bEQ path, you only need to create one model. And you create that one model based upon the rules in Appendix G for creating the proposed design model. And your source energy usage index for that model is calculated. Then it's divided by a median source energy EUI that's determined using Zero Tool, which we'll talk about that later in the presentation. And that calculates a performance score. And your tier is determined based upon your performance score. So you can see here, if your performance score is less than or equal to 59, you hit tier 3 and you achieve the highest level of savings. Okay. All right, so that was just a brief description of the two paths for showing performance in the program. So now I want to talk about pre-design energy modeling and when it is typically used. So at the very early stages of a project design, the level of effort associated with modeling is very low. There aren't many features in the design that have been decided, so it's very quick and easy to create your model. You're not fine-tuning building envelope features. You're not fine-tuning all the different space types and how you're used. The level of effort is relatively low, but your performance impact is large. And that's because these design features have not been solidified yet. So there's a lot of room for making design changes. But as time goes on, the level of effort for creating the energy model increases because now you've got to capture all the space types as they've been designed. You have to capture all of the nitty-gritty elements of the building envelope that have been designed. And it's more of an effort, but it's less impactful. There are less features that you have the ability to offer input on because they've already been determined. So typically, and there's a chart here. Let's get the pen out. So there's a little chart here from this is from the AIA 2030 commitment 2014 progress report. And this shows us that basically for 55.8% of projects, they're not modeled at the concept or schematic design stage. And then compared to 44.9% of projects are not modeled at I think a better way of saying this would be at the concept and schematic design phase, 44.2% of projects are modeled versus a greater number, 55.1% of projects are modeled at the design, development, or construction documents phase. So we can look at the data and we know that a lot of projects are missing out on these early design opportunities because they're not being modeled at these early stages. And all too often a project is scrambling, and I'm sure if any of you are modelers or part of design teams, you've experienced this. A lot of times projects are scrambling to meet their energy performance goals because it's so late in the design. You're not able to change, make large changes to geometry or building orientation or window to wall ratios, things that can have a large impact. And if you had started earlier in the process, those elements of the design could have been optimized. Okay, so a standout finding from the AIA 2030 commitment report, and AIA is the American Institute of Architects, is that projects using energy modeling predicted an average of 16 percentage points more energy reduction compared to projects that won't be modeled, that aren't modeled. So energy modeling has been demonstrated to have a very large impact on the performance of buildings, and the AIA made statements in this report about how important energy modeling is going to be and is in hitting performance goals associated with many of the goals that different jurisdictions and things have throughout the country, as John talked about in his presentation with regard to New Jersey, and it's really stringent goals for the future. Okay, so in terms of the program, as I mentioned before, because early design modeling is so beneficial, the P4P new construction program offers a pre-design bonus incentive of 4 cents per square foot. And not only can this help offset some of the additional cost of paying for the early energy modeling, but it can also help achieve a greater incentive down the line because of the improved building performance that you can achieve by using the early design modeling. Okay, so like I said, the program has this pre-design bonus, and the requirements are outlined in the partner guidelines, and they are loosely, or I wouldn't even say loosely, they're based on ASHRAE Standard 209. So what is ASHRAE Standard 209 for those of you that aren't familiar? It describes a methodology to apply building energy modeling to the design process. And it covers from concept phase all the way through to post-construction. Today we're going to focus on concept construction documents, but the standard is rich with helpful information. And the key takeaway is it's best to start early. And full compliance with the standard is not a requirement for the pre-design bonus. So today you'll see requirements and little notes about the pre-design bonus in this little red cloud that you see here. And the standard is great because it provides tips in terms of, you know, what is important to capture at each stage in the modeling process. For an example, and we'll talk about these different modeling cycles in a minute, but you know, at the concept phase, it's not important to capture detailed HVAC zoning. I mean, that's not even established yet. So it helps with determining what parameters and how should I capture them in my models throughout the stages. All right, so now we're going to talk about these phases and different modeling cycles. All right, so on the left on this slide, you'll see the general requirements from Standard 209. They're also part of obtaining the pre-design bonus. And on the right, we have the modeling cycles. So simple box modeling and conceptual design modeling typically occur concurrently or before the items in the general requirements at the concept stage. So you'll be using these modeling cycles, the simple box model and the concept design model, to inform the climate and site analysis, benchmarking. That information from these models will be part of the discussions at the energy charrette. And that information will also be used to help set the performance goals that'll be captured in the owner's project requirements. And we'll talk about each of these stages in more detail throughout the presentation. So we'll begin with the climate and site analysis. So this is where you want to look at all of the parameters associated with climate and the site where the building is supposed to be located. So you'll create a list of these different parameters and a list of potential strategies to adapt to the site conditions. So a simple box model can help identify the most impactful parameters associated with the site and how they affect the end use breakdown and the peak heating and cooling loads. And we'll discuss how the model is integrated with the site analysis when we talk about the box modeling cycle. So next, and I'm obsessed with benchmarking, is the benchmarking stage. I think this is essential really for coming up with your goals and understanding the different measures that you want to include in your project. So benchmarking is so that you can understand the performance of typical buildings in the same climate zone of a similar type. And like I just said, it prepares the groundwork for setting the goals for the project. So how would you know whether to have a goal of an EUI of 50 versus 100 unless you had something to compare it to? And there are a few benchmarking resources on this slide. So there's ASHRAE 2030 Zero tool, and we'll talk about that in a little more detail when we discuss bEQ. And there's EPA Energy Star Portfolio Manager and also Target Finder. I'm sure many of you are familiar with those tools. They're commonly used. Both the EPA tools and Architecture 2020 can help determine the median site and source energy EUI for a building of a similar type in a similar climate. So those will give you the median EUI. Then we've got the, and these are all links, by the way. So if you download this presentation, you can click on these hyperlinks and actually go to the websites. So then we have the PNNL/GOE prototype models. And these are great. So these are models created by PNNL and GOE. And there's different building types. And they're created for different vintages of 90.1. So for an example, there's a prototype model for a large office building for 90.1 2016, climate zone 4A, and it will give you the end use breakdown of that building. So you can get a feel for the source energy and site energy consumption of an office building, if your building was an office, within your climate zone for your code vintage. If your code, like it is in New Jersey, was 90.1 2016. So that can set sort of the floor for your performance. And then we have ASHRAE 1651 RP. And this I'll talk about a little bit more on the next slide, but that's to help you set the lower limit of those EUIs. And in order to be eligible for the pre-design bonus, the project must be entered into EPA's Target Finder. So what is this ASHRAE 1651 RP? So there's an ASHRAE research project report called Development of Maximum Technically Achievable Energy Targets for Commercial Buildings. And for the project, a list of energy efficiency measures was assembled for commercial and multifamily buildings. So the list included both commonly used and cutting edge energy efficiency measures. And the goal was to be comprehensive of the measures that are out there. And then models were created that included these measures to determine what is the minimally achievable site EUI for different building types. And you can see these listed on the slide for different climate zones. And so this is a great resource for setting, okay, like how low can we go in terms of our performance goal for the project? This is also really useful for net zero feasibility planning and sort of understanding, you know, what can we expect in terms of the lower limit of the site EUI for the building, and how much energy are we expecting to be able to produce? Okay, so once you've done your benchmarking, you have the energy charrette. So that's a meeting with stakeholders, the design team, and anyone else relevant. And a charrette is just an intense design and planning meeting. So the energy charrette is required for the pre-design bonus and must be conducted prior to initiating energy modeling. And throughout the presentation, you'll see references to the guidelines in this blue color here. So who should be there? Of course, the owner, the architect, any relevant engineers that are part of the design team, the P4P partner, if that's different from the energy modeler, or the supervisor of the energy modeler, any other relevant members of the design team, and any relevant contractors. So basically, try to get everyone in the room when you hold the charrette, because that's when it's most effective. You want to get everybody on the same page, working together for common goals. And that's what we'll talk about. So what are the goals? So I'm only going to talk about these on a high level. If you visit the partner guidelines, it lays these out nicely for you. But number one is you really want to develop a common understanding of the purpose of the energy modeling being conducted. You need to figure out what the project baseline is. Is the code 90.1 2016? Is it 2013? You really want to make sure you're all on the same page with that. You want to talk about the operating conditions that the owner and the design team are projecting for the building. And you want to compare this to the assumptions in Target Finder, because you want to make sure you are using an apples to apples comparison when you look at the median EUI that you're comparing to, and your target as well. You want to look at the end use breakdown for a building of this type and climate zone. And this is where the simple box modeling comes into play. And we'll talk about this a little later, but doing your simple box modeling will give you the end use breakdown for a building in the location and climate zone. You want to set your performance goals and metrics, and you want to do this on a whole building level, but you also want to do this for specific components and systems as well. You want to brainstorm different energy efficiency measures. The design team is always thinking of things they want to include in the project. So this is a great opportunity to get everyone on the same page. You want to set and determine which modeling cycles will be completed for the project. And you want to talk about how are these going to be used to inform the design. It's a wasted effort, right? If you say, okay, we're going to do these modeling cycles, and then a report is created and no one looks at it, or it's not actually incorporated into the design. So it's very important to lay out how and when are the results of the modeling cycles going to factor into the design, and what parameters are they going to help set and address. You want to talk about whether there's any financial criteria. So, a building could have every single energy efficiency measure in the world, right? But there are financial constraints and there are financial goals. So you want to lay this out at the start. You want to talk about, if first cost is going to be part of the analysis, you need to figure out, okay, so what's the financial criteria and who is going to come up with this first cost? Is it going to be the design team? When are they going to provide this information? And that factors into number 11, which is you want to have set a project schedule and the milestones associated with each point on that schedule. And also incorporated into this schedule, you want to set the responsibilities and the processes. Okay, so on this date, the goal is for the mechanical engineer to provide cost estimates for 3 different HVAC options. Things like that. So responsibilities, dates, and then financial criteria are very important. Okay, so like I said, the energy charrette is required, as I said here, with the little red cloud. And there are 2 tabs in the ERP that can both help you with the energy charrette because they cover the different items that you want to cover in an energy charrette, but they also have to be filled out for the program. So there's the P4P energy charrette tab, that one. And then there's the P4P energy charrette end uses tab. And the charrette tab covers a lot of the information I just talked about. So you could document it on that energy charrette tab and include the tab in the owner project requirements. The end use tab helps you with the benchmarking process. So it's right there for you. So you don't have to go digging too far. So what are the owner project requirements? So it's a written document that details the owner's requirements and goals that are deemed necessary for the owner to feel that the project has been a success. And there are many items that need to be captured in the owner project requirements. You can see the partner guidelines here in blue for more of these details. But you know, at a very high level, the energy performance goals must be documented, and you must include the P4P ERP tables that we talked about. So the energy charrette, you also need to include the general information tab. And it's important to update the owner project requirements as you go through the design process and things change, so that we can make sure everyone is on the same page and that they're aware of things as they develop. Okay, so now we'll move on to talking about the energy modeling process flow. We just finished the general requirements during the concept design stage, where you do the charrette, the owner project requirements. Now we'll go through the actual modeling that occurs. We're going to touch on each of these. First, I just want to point out, though, that in order to receive that pre-design bonus, you need to complete both or either the load reduction modeling, including the simple box and conceptual, including elements of the simple box and conceptual design modeling cycles, and or the HVAC system selection modeling. So we'll discuss these in more detail on the following slides. All right, so the simple box modeling. So you create energy models to calculate annual building energy by end use and to get a feel for the peak heating and cooling loads. You keep the HVAC systems identical between models. And the idea is you're performing a sensitivity analysis by varying building site characteristics and different building characteristics to understand what is impactful. So you can use the site parameters identified in the climate and site analysis item that we talked about earlier. And you want to use anticipated schedules and plug loads. If those aren't known, you can use a source like ComNet. So it's required for the P4P pre-design bonus for the load reduction modeling that you identify the distribution of energy by end use. And that's an element of this modeling cycle. So you want to evaluate the effect of these different elements on the peak heating and cooling loads and the annual energy consumption and end use breakdown of the building. So the timing is before and or simultaneously with the energy charrette. So here's a shading example. So we've got our building in the picture, and there are a bunch of buildings around it that are shading it. The building that's highlighted includes electric heat and daylighting controls. So, you know, in order to understand this impact of shading, you can create an energy model with the shading, and their expectations are that it will reduce daylighting opportunities and therefore increase lighting energy consumption because the windows will be shaded. There'll be less solar heat gain, so there'll be decreased cooling energy, but increased heating energy consumption. And so to understand how impactful this is, because let's say you had a similar building that you did recently, and you notice that you got pretty good daylighting savings and a lot of HVAC savings. Well, you would want to know how is the scenario different, or how does it differ from the benchmarks? So in this example, we ran a model with and without this shading. And as expected, we found that with the shading here, so this line here, you can also look at it in this chart form where blue is no shading and gray is with shading. And you can see, it's probably easier to look at in the chart form up here, but you can see that with shading that the fuel used for space heating is higher than without shading. And then space cooling, with shading, the space cooling energy is a lot lower. And so we can see that this shading has a significant impact. It has a little impact on lighting due to changes in the amount of daylighting control opportunities. So this will give you a sense of what is the effect of this site characteristic that we're dealing with in this project, and how sensitive is the end use breakdown and the peak heating and cooling loads to this site factor. And in terms of this example here, you can see the peak cooling load was reduced from 844 kBTUs per hour to 776 kBTUs per hour with the shading. So there was a nice reduction in peak cooling load. But then we saw a large, see this here, 25.8% increase in space heating energy usage. And then a 16.2% decrease in space cooling energy usage. So this is quite an impactful one. And then same with fans, quite a reduction in fan energy because this is an office building and it's very much affected by cooling, and the fans are going to not operate as much if the cooling load is less potentially. So anyway, so this is the type of analysis that you would do for the simple box modeling cycle. Then you have the concept design modeling. And this is where you want to evaluate opportunities for reducing energy consumption and peak loads tied to the architecture and form of the building. So you're not just trying to get a sensitivity analysis and look at the end use breakdown like you were previously. Now you're trying to compare different architectural options. And this is required for the P4P pre-design bonus in that you need to compare, I believe it's at least two, double check in my partner guidelines, architecture or building form related options. So there's a note in ASHRAE 209 that this cycle can be skipped if the building is dominated by internal loads. So let's say you had like a process production facility or something related to industrial process. This wouldn't be it wouldn't be a cost-effective use of the modeling effort to spend time looking at the architecture of the building because it's dominated by process loads, not HVAC. So this is conducted prior to the beginning of the schematic design phase. So of course you want to do this before the form and architecture of the building has been set. So this needs to be done where those design parameters are still subject to changes. So let's do an example. So we want to compare the annual building energy consumption by end use and the peak heating and cooling loads across two orientations for an office building. So how does the orientation affect these parameters? So we have our east-west orientation where the building is elongated along the east-west axis, and we have the north-south orientation as well. And we can see that, and this is consistent with all the design guides and recommendations out there. We can see that the east-west orientation performs much better in terms of reduced heating and cooling peak loads, along with reduced space heating, space cooling, and fan energy consumption. And this has to do with many things. You can check out the design guidelines for more information on this, but essentially it has to do with the angle of the sun across the different orientations. But as you can see, this is a very important factor. And this, with an ASHRAE 90.1 Appendix G model, this will definitely affect performance, because for setting the baseline, you need to model the building with each orientation. So rotated by 90 degrees, and then average them. So if you pick an inefficient orientation for your proposed model, it's going to hurt you. So as we can see here, this was with these percentages. So a negative means that with the north-south orientation, energy increased. So when you look at these percentages, they mean energy increased. So from going from east to west orientation to north to south, we had increases across the board. You can see that here. Sorry, I don't want to cross them out. So this is very impactful. And thank goodness we did this modeling at the early stage. So then there's load reduction modeling. And here we want to evaluate at least 5 strategies that will reduce annual energy use and heating and cooling peak loads. And you want to identify the distribution of energy by each end use for each strategy. So examples include, but they're not limited to, evaluating insulation levels, window to wall ratio, shading, natural ventilation strategies. There are many different options. And this needs to be completed prior to or during the schematic design phase. And as I said before, partners must complete either this and the elements of the simple box and conceptual design modeling that I just discussed, or the HVAC system selection modeling in order to be eligible for the pre-design bonus. So when you do your load reduction modeling, you want to use, and this is similar principles apply to the simple box and the conceptual design modeling as well. You want to use simplified perimeter core zoning. The modeled HVAC system type, you can either use the 90.1 Appendix G baseline or your expected proposed HVAC system type. And you want to model the other parameters like envelope, surface water heating efficiency, and lighting to be minimally compliant with the state code, or let's say the owner has targets for these, then you can use those as well. So in terms of reporting, you want to make sure that you report the energy consumption by end use and the peak heating and cooling loads for each of the alternatives that you analyzed. And then you want to include recommendations and at least 5 strategies for reducing load. If projects have high internal loads, you want to make sure that at least 2 of the recommended strategies are related to reducing those equipment loads. You don't want to neglect high impact end uses. Okay, here's an example for this one. So we have our base case, which is a 3-story office, 2-to-1 aspect ratio, has a 25% window to wall ratio, and daylight dimming controls. So the alternative that we want to look at is the same as the base case, but with a 40% window to wall ratio. And we want to understand what are the energy impacts of the higher to window to wall ratio. So let's say the owner is really committed to energy efficiency, but they also they love windows and they want to provide the occupants with plenty of sunlight and they want views of outside. So they're curious. They want to know what's the impact of increasing the window area. All right, here it is. So, well, what we find is this is a very impactful design decision. And it's also impactful for Appendix G projects because the baseline window to wall ratio is set in Appendix G. So if you exceed that, that's going to depending on the building type, that will provide a significant penalty to the project. So like I said before, like you can look at it in chart form up here or in this table form. But looking at the table, so we've got a line that shows the energy consumption and peak heating and cooling loads for the 25% window-to-well ratio. And then below that is the 40%. And then below that's the percent difference with negative numbers showing an increase in energy consumption or peak loads. Well, we can see this is very impactful. The peak heating load increased by 23.6%. The peak cooling load increased by 17.4%. Had a little bit of an impact on daylighting in our project. And then the actual energy consumption, we also see big increases. The most impactful being fans, where we see a 21.4% increase in fan energy consumption. So this is high impact and a measure that definitely want to take a look at these early design stages. All right, so the next modeling cycle, and like I said before, for the P4P program, either what we just discussed, the load reduction modeling cycle and the simple box and the conceptual model are required, or the HVAC system selection modeling. And I find this very fun to model. So you want to complete this after the load reduction, if it's applicable, and you want to evaluate at minimum at least 2 different HVAC system types. And you want to estimate the annual energy and demand impacts of the different options. So you want to do this prior or during design development, but before the HVAC system type has been selected. Makes sense, right? So in this scenario, your modeling parameters, you can still use perimeter core zoning, representative of the building design. So in terms of your percent breakdown of spaces that you apply to the model, you want that percentage to be representative of what you're actually going to see in your building. So then again, same principle with the other components, either minimally compliant with code or in line with the targets for the project. When you do your HVAC system modeling, you want to set your efficiency at the minimum required by code, and the minimum required by code in terms of controls, unless those controls are being evaluated as part of this analysis. And you don't want to neglect ventilation strategies. So you want to look at things like, should we include a dedicated makeup air system or a direct outside air system, and demand controlled ventilation. You want to look at these strategies when you're doing this analysis because they have a large impact. And reporting, same thing. Energy consumption by end use, your peak heating and cooling loads, and then your recommendations. And you want to show the results of your analysis. And you want to include those ventilation strategies in your recommendations because they are of a high impact and they're very important. So let's do another example. So we're going to, this example compares HVAC design alternatives for a major renovation of a high school. So we're going to compare a baseline, which is just VAV. So it's the ASHRAE Appendix G baseline, then optimized VAV. So this would be a variable air volume system with condensing boilers, an air-cooled chiller with magnetic bearings, and improved controls, so all the bells and whistles with controls. We're going to compare that also with a chilled beam system that also has condensing boilers and has those high efficiency air-cooled magnetic bearing chillers. But that includes a constant volume dedicated outdoor air system. And then lastly, we want to look at a variable refrigerant flow heat pump system with a variable volume direct outside air system. So these are our 4 systems that we want to look at and compare. So let's look at the results. So this is always fun, right? So interesting to look at how these different options compare. So on this graph, you'll see on the y-axis, the annual energy cost. On the x-axis, you'll see the different systems I just talked about. So the baseline VAV, the optimized VAV, filled beam with the constant volume DOAS, and then VRF and the variable air volume DOAS. So some takeaways here. The optimized VAV and the VRF with the VAV DOAS were the top performers in that they had the lowest annual energy cost. Another takeaway, and you might be wondering, oh, the chilled beam didn't do very well. What's going on there? Well, I suspect that this large bit of gray here is because it's a constant volume DOAS. So you're losing out on some savings by delivering a continuous and constant amount of outside air, versus with the VRF with a VAV DOAS, you're getting savings because by using demand controlled ventilation to reduce outside air, you're lowering heating and cooling loads, and you're also getting fan energy savings. So it would have been also interesting to look at how this option here would have compared with, an option with filled beam, but with a variable air volume DOAS. So that would have been interesting. What else? What else is interesting here? So I think another interesting piece is if we look at the variable refrigerant flow example, this guy, and we look at the cooling and compare it to the cooling with the optimized VAV, we see that there's significantly less cooling with the optimized VAV, which makes sense, right? Because you've got chillers with the optimized VAV, which tend to have a higher efficiency, especially the ones modeled here, than a DX variable refrigerant flow heat pump system. So that makes sense. And you're always doing that, right? When you conduct analyses, you're looking at the results and you're asking yourself, do these make sense? Is this what I expected, right? So, and lastly, the other thing I thought was interesting about this analysis was, so compared to the optimized VAV option, the chilled beam and constant volume DOAS had higher pumping energy in green. That's right here. And I think that's because of the increased pressure drop due to all of the coils associated with the chilled beam system. And also, yeah. So, yeah, interesting analysis. This is always fun. I love it when a client wants us to incorporate this into the modeling process. And I think it's extremely beneficial for the clients, especially when you incorporate first cost and some life cycle cost analysis as well to figure out which option is best. And real quickly before I leave this slide, the other thing I found interesting was just the heating energy consumption, or not energy consumption, but cost between the optimized VAV, so this orange here, and the VRF. The VRF is slightly lower, and I think that's only because, so to remind you, the optimized VAV had condensing boilers, and then the VRF obviously has VRF for heating. And while VRF, the heating EUI, site energy, is probably very low compared to the condensing boilers, but because electricity is more expensive than natural gas, you don't see quite as much savings as maybe you would think using such a high efficiency heating system. So that's an interesting piece as well. So here's just an overview of some strategies to help with incorporating efficient elements and thinking of things to compare. So what do we want to compare? So here are just some points. In general, high performance HVAC systems generally, so let me back up here. When we look at high performance buildings, which we will do in a little bit, And we look at, okay, what do they include? What kind of strategies? We tend to see geothermal heat pumps and a combination of, like we just looked at, the VAV, direct outside air units, and VRF. So we tend to see those kind of systems in high performing buildings. And typically those are employed to achieve net zero, because like I said before, those will help you really get your site EUI down, those heat pump systems. So some ventilation strategies, so energy recovery with high effectiveness, definitely demand-based ventilation, economizers, and then natural ventilation strategies. So we'll see in a few slides that some really high performing buildings have automated windows that will open up when outside conditions are good for providing natural cooling or natural ventilation. Variable speed pumps and fans, static pressure reset controls for VSD fans, differential pressure reset controls for VSD pumps, and then intermittent cycling indoor unit fan operation. So what that means is decoupling your outside air from the system that provides heating and cooling. So this is basically your as an example, your VRF system, where you've got your fan coil unit or evaporator, people use different terminology, in the space providing just heating and cooling. And those evaporators tend to have really low fan power. And they cycle during occupied hours, they just cycle on and off with the heating and cooling loads. And then to meet the outside air requirements, you'd have your variable air volume, direct outside air unit decoupled from that evaporator, providing that outside air. And you would do that using demand controlled ventilation to reduce outside air levels when occupant density is reduced. So that's found to be a very high performing strategy. All right, the next stage is design refinement. So the building form and orientation and the HVAC system type and surface water heating system types and the space types have been set at previous cycles. And now you use energy modeling to refine the design. And per standard 209, you do this for at least one building system listed here, and it's not limited to those, but you want to focus on at least one building system during this modeling cycle. And you want to do this before the end of the construction document stage. So let's go over an example to illustrate what kind of things, or an example of something that you would do at this stage. So here's an example of HVAC mapping for a dedicated system for a critical zone. So, and this is a school case study. So what does this mean? Okay, so our initial proposed design has two multi-zone variable air volume units called MZ-VAV, and they're split up. So there's two of them, one serves the north and one serves the south end of the building. Now, the system for these two systems, the minimum ventilation ratio, so minimum ratio of outside air to supply air, and the minimum supply ratio, so the ratio of supply CFM to the design supply CFM, we find through energy modeling that they're both being dictated by the ventilation requirements, and you don't even really need energy modeling to figure this out. You can kind of figure it out by just looking at the design drawings as well, but they're being dictated by the ventilation requirements of a critical zone associated with each system. So what do I mean? So for an example, one of these multi-zone VAV units has a workshop area that has very high ventilation requirements. And so the VAV unit is not able to reduce its minimum supply ratio past a certain point, because it's the critical zone is always like, I need more, and the control sequence is such that that critical zone is setting that supply ratio. And this is not optimized. So what can you do? Well, in this scenario, what you can do, and what this is showing here, is basically you can give that workshop, you can give that critical zone its own variable volume single zone unit. And so that single zone unit will operate, and it will meet the high demand for outside air required by that workshop. And it will allow, and then it will be, so that zone is now not part of that original multi-zone variable air volume system. And now that multi-zone system can operate at a lower supply ratio because it's not being governed by that critical zone anymore. And so by doing that, there's pretty decent fan, heating, and cooling energy savings by giving that that zone its own unit. And it reduces, like I said, it reduced the supply fan ratios on that original unit, allowing for fan savings. And it allowed for lower outside air rates to be provided to the other zones that are part of the system, which reduces heating and cooling loads. The other element here is that with the single zone VAV system, you can reduce the design fan power a little bit because you can locate it, you can reduce the length of the ductwork and remove the zone reheat coil, because now it's a single zone unit, so it doesn't need a reheat coil, which reduces the pressure drop. And so you can get some fan savings because there's not as much pressure drop in that system. There's a tiny pumping penalty to accommodate the new hot water and chilled water coils that will be in that additional system, but relatively insignificant in the grand scheme of things. And actually, when this was modeled, we saw $3,844 of energy cost savings. So it was pretty, it wasn't insignificant. And this is just a graphical depiction of the, the top graph is the minimum flow ratio when the workshop was part of that multi-zone VAV system. So the minimum fan ratio only dropped to 0.68. Once we removed the workshop from that multi-zone system and gave it its own single zone system, the fan ratio was able to drop to 0.53 for that multi-zone system. So good savings, good results. So that's an example of design refinement. So we know the HVAC system types. Now we're looking for opportunities to refine the design and achieve even greater savings. And so the next modeling cycle, which I think you're all familiar with, so we won't go into as much detail on this modeling cycle today, but this is where you quantify and map the energy performance of each building design aspect that contributes to project performance. So items that contribute to energy savings. And then you also map items that contribute to an energy penalty. And so this is essentially your list of measures in the design, including items that result in a penalty, kind of like we have in the ERP when we have our list of measures. And when you do this, and I'm sure a lot of you, so I think this is the general way that modeling goes, unfortunately, and hopefully that changes. But the HVAC system type is set, the building form and architecture is set, and you're giving design documents, and you map all these measures, and you come up with, okay, well, I've thought of some additional measures, and you include those in your analysis. So I'm sure you're all familiar with this. So This is often around the time when a project submits or is preparing the proposed design ERP. And I'm sure many of you, you've started to prepare the ERP, and then you go, you know what, I think they can get some extra savings with these other measures. So you go to your design team and you let them know, and then they decide whether to include them or not, and then you might update the ERP with the measures. So I think a lot of you are familiar with this modeling cycle. And then lastly, the last modeling cycle from concept design to construction design is energy simulation aided value engineering. So this is where the modeler looks at items on the table that are proposed to be changed through the value engineering process. And so anything that it will affect, so anything that is likely to affect the performance goals, you would incorporate into the energy model to see, okay, how does this change to the design affect our performance goals? And it'd be great to include the first cost so that you can do an economic analysis to look at, okay, well, that might be a less expensive option, but you know, the annual energy operating costs are much more expensive, and it actually economically doesn't make sense. So that's the type of analyses that you do at this stage. And I'm sure all of you are familiar with this, where you know, you do a model, the design goes away, and then it goes through value engineering outside of your site, and then they come back and they say, oh yeah, we got rid of the VRF and now it's P-tax or something, and it's like, no, that's going to hurt performance. So you know, it's very important to have the modeler involved in this stage. All right, so the next section will be case studies. Now we'll go over some high performance case studies to give you an idea of the design strategies that result in high performance. So the whole reason that we're doing or promoting, you know, the early design modeling is to achieve high performance and to help design teams and owners meet their goals, right? And so it's important to understand the strategies that should be analyzed and looked at each of these stages in order to meet those goals. So let's look at a few examples of high performing buildings. So this is an example of a hotel in New Haven, Connecticut, climate zone 5A. I tried to find examples in our climate zone. So the owner engaged the energy modeling before the schematic design phase for this project. The project participated in Connecticut's whole building incentive program. But the project, like I said, is a hotel. It has 7 above grade stories. It's actually an existing building. As you can see, 110,000 square feet with a 5,600 square foot restaurant, 125 units, and it achieved approximately 40% source energy savings over ASHRAE 90.1 2013. So very impressive, awesome project. So what were the design elements here? So these are the measures. So it had a direct outside air unit with energy recovery serving all spaces in the building. And it had high effectiveness values, so approximately 88% enthalpy effectiveness. It had VRF, variable refrigerant flow systems, serving all spaces in the building. Very low fan power on the terminal units. And like we talked about before, the terminal units cycled with load. The fan power was less than 0.15 watts per CFM. They had this cool strategy where, so they knew based on hotels in their portfolio that roughly they would experience like a 75% occupancy rate. So they felt they could pretty accurately predict that at any given time, they would have approximately 25% unoccupancy. And so they have the system whereby they can schedule the ventilation. So they would have blocks in the hotel that would just shut down in terms of heating and cooling and outside air during periods of time. And they would shift these blocks such that 75% of the units, the hotel units, were always active with 25% inactive. And they could use their, I guess you call it a building management system to do this. So they achieved savings that way. They had completely recirculating kitchen range hoods. So they weren't bringing outside air into the kitchen. They had heat pump water heaters, low flow fixtures, 0.5 GPM faucets. They had ozone laundry systems, Energy Star kitchen equipment, lighting, all high efficacy LED, power over Ethernet lighting controls, very excellent envelope measures, so very low window U values, very aggressive leakage goals. So you can see here 0.084 CFM per foot squared at I think that's 75 PSA compared to 0.4 for Appendix G. Did I say PSA? Pascals. Better than code roof and exterior doors. So just a lot of measures, and it performed really well through the modeling effort. And this one, you know, the modeler was constantly trying different things and really working hard with the design team to optimize this design. So this is from the ASHRAE Advanced Energy Design Guide for small to medium office buildings. And it's an example of an office in Seattle, Washington, climate zone 4C. Not quite ours, but a little close. So it was a 6 above grade stories, 52,000 square feet, and it was a new construction project. So the predicted site UI is 16. Wow. The achieved actual site UI is 12. So as a reference point, the PNNL prototype for an office in climate zone 4C, site UI is 27.2. So this building performed exceptionally well. So what measures did they use? Well, HVAC, closed loop ground source heat pump, and they had radiant floor heating and cooling serving office spaces. So reduction in fan energy. Ventilation was provided by a direct outside air unit with energy recovery. They had passive cooling and natural ventilation. This was through those automated operable windows that I talked about before. Low flow fixtures, high efficacy LED, and then they had additional task lighting. So task lighting is great because that can be just used only when needed. So you're not keeping a space lit when an occupant is in there, and maybe you don't need your task lighting. Maybe you're not doing something that requires those extra lumens. So it also had tall, high windows to optimize daylighting controls. So if you use tall windows, and the window area doesn't have to be large, you can optimize daylighting while reducing solar heat gain. So this project strove to do that. In terms of envelope, it did have pretty high performance windows, 29% window to wall ratio, better than code roof, but it had these automatic external operable shades. And the thing with an office has high internal loads and it has low nighttime occupancy. So generally, in our climate zone and warmer climate zones, the focus is on lowering that solar heat gain and the internal gains. So shading is often a very important measure for high performing office buildings. Actually, you know, in terms of building envelope, in some climate zones, because the internal gains are so high in an office, an envelope, if you have an envelope with too high of an R value, you can actually hurt performance because you're trapping, you could be trapping heat inside the building such that the building is warmer than outside. So in an unwanted fashion. So you don't want to do that. So envelope is less important, a little less important, or when I say envelope, like U values, things like that, they're a little less important for an office building. And that's why it's very important to do this early design modeling, because you want to run your models to make those decisions, right? You can't just say, oh, just give me the best of everything, you know, because there are complex interactive effects depending on your climate zone, your site conditions, and your building type. Here is an example of a school. This is our climate zone 4A, Arlington, Virginia. And this is from the ASHRAE Advanced Energy Design Guide for K through 12 schools. 2 stories above grade, about 100,000 square feet, new construction, and it's an elementary school. So again, this one, really impressive performance, predicted 21.1, actual 15.8. And then again, with this reference value, this is the PNNL prototype school, climate zone 4A for vintage 90.1 2016. And that was a 42.8. So really just impressive performance. So what did this design include? Well, it included ground source heat pumps. Once again, ventilation provided by a direct outside air unit with energy recovery and demand controlled ventilation, local thermostatic control, low flow fixtures, any energy efficient laptops, water source refrigerators. So in a school, there is generally, like when you look at the prototypes, for an example, a relatively high miscellaneous EUI, and that's generally because schools have cafeterias where you have cooking equipment, refrigeration equipment. So it's important not to neglect that equipment as well. High efficacy LED, daylight switching zones with dimmable LED, high performance windows. Again, similar to the hotel, aggressive leakage goals for infiltration. So 0.11 compared to 0.44 with Appendix G. Also better than code exterior walls. So the takeaway here is there are some commonalities, right, with these high performing buildings. So we see a lot of direct outside, I think every one of these had a direct outside air unit with energy recovery. So the outside air was decoupled from the systems that provided the heating and cooling. Demand controlled or natural ventilation, high efficacy lighting. Then an effort to maximize lighting controls was also present in all of these strategies. High performance windows, low flow plumbing fixtures were present in all of them. And the big one, heat pump HVAC systems. So the hotel had VRF. The office, I believe, had a ground source heat pump system. And then the school also had a ground source heat pump system. So yeah, all heat pump systems. And so this sort of ties in with our next discussion of bEQ in that with an Appendix G model, your baseline is going to be gas. And then if you have a heat pump, your proposed is electricity. And some people have a concern about their performance because of that, since electricity is a higher cost on a $1 per kBTU basis than natural gas. And also the source energy factor is higher for electricity compared to natural gas. So sometimes people are concerned about that in terms of performance when using Appendix G, but with bEQ, there's no fuel switching. So that might be a more attractive option. So first I want to touch on some resources and then we'll talk about bEQ. So these are just some resources to help you come up with ideas and best practices for high performance buildings. So we have the design guides, that's where some of our case studies were from. ASHRAE 90.1, so it is another resource. If you go to the 2019 version, for an example, that can be a good resource. Then there's this ASHRAE standard 189.1, so the standard for the design of high performance green buildings. It's a great resource. Then the New York Stretch Energy Code, which was developed, so it has more stringent requirements than 90.1 2016. So, and that's based on the cost effectiveness of different components. So that's a good resource to consult. And then this is what I talked about earlier. So this report with the minimally achievable site EUIs, well, that's, if you go to that research paper, you can look at the different measures that were included as a place to get ideas. And then also, I don't think I mentioned this, the Building Innovation Multifamily from MBI, this guide as well, which focuses on multifamily, is a good resource to consult. All right, so we'll finish up with a discussion of bEQ. So as I said earlier, there are two paths, Appendix G and bEQ, for demonstrating compliance with the P4P program. We saw this slide earlier, but I just wanted to remind you of the basic concept of bEQ. So you create one model, just one, and you do have to run parametric runs, and we'll talk about that shortly. But you create your proposed design model, and you create that following the rules in Appendix G and 90.1 for the proposed design. Well, we'll talk about that in the next slide. So then you get the source EUI of your model, and you divide that by a median source EUI, and we'll talk about how you get that. Multiply by 100, and that's your performance score. And which tier you fall into, and the tiers determine your incentive level, depends on your performance score. And gut rehabs have slightly different scores and tiers, just like Appendix G, things are a little bit different, but here it's for a new construction. What's shown here is for new construction. So the bEQ modeling protocol. So what I said on this slide was you develop your model using the rules in 90.1 Appendix G for the proposed design. So what am I talking about? So in table G3.1, we've got our baseline, we have our proposed columns. So you follow table G3.1 proposed design column when creating your model. So if you have things like an area where lighting is yet to be designed, and you say, well, I don't know what to put there, it's not designed. Well, you would consult table G3.1 for how to treat that in your bEQ model. So in terms of modeling data, you would use the schedules, plug and plot process loads specified by ComNet in appendices B and C. The exception would be for multifamily, where you would use the multifamily new construction program guidelines. But it's very important that the schedules that you use are the ComNet schedules, and not even like what you think the building will operate like, because you want to compare apples to apples, and those targets, those scores, these tiers and these scores are based on assumptions about building schedules, plug and process loads. So you need to use the ComNet schedules. and you go to the bEQ. They even have a bEQ data tab for you in the ComNet appendice spreadsheets. The bEQ documentation. So it's a little actually simpler than Appendix G. So in the compliance form on the general information tab, keep the default that says ASHRAE 90.1 2016 Appendix G. That's okay. Just leave the default. You don't have to fill out the results from eQuest tab. You don't have to fill out compliance calculations tab. And for all other tables and tabs, all you have to fill out is the proposed design information. You do not need to fill out baseline information. So you can skip a whole tab for HVAC as is shown here. Baseline is crossed out. It's not applicable. So you just fill out the proposed information in the compliance form. All right, so let's talk about how to determine your median EUI. So the program, the P4P program, calculates the project's bEQ score within the ERP. And like I said, it compares the model source energy EUI of the proposed design and the median source energy EUI as determined by Zero Tool. So in order to figure out what that median EUI is, you need to fill out Zero Tool and enter the median EUI that it spits out into the ERP. So here's how you do that. So this is a screenshot of what the Zero Tool website looks like. So at the top, you want to fill in your building name and address information. So there's an example shown on this slide. Then you want to make sure you select new construction in this box here. So then you want to, in the building use details, you want to select the primary building use and specify any additional building uses, selecting one by one, where it says add another use, okay? And you're not, so if you're building, let's say it's, I don't know, a hotel, and there are storage rooms and corridors, you don't go separating every little different space type out. Only if there's an area that is just significantly different from your primary building type. So for an example, if there's a parking garage, an unconditioned parking garage, that should be entered as a separate building type in here. So you should add a parking garage, add another use, you should add parking garage. Then you complete the building use detail section, this one here, this box, using values consistent with your as designed model. And I've filled that out here for this K through 12 school. So then at the bottom, so this is where you filled out, up here is where you filled out the information about walk-in refrigerators, just that information consistent with your model we just talked about. So then down here, you hit calculate baseline and target. And right next to where you just entered all the information, it'll give you your source EUI. So this is the median source EUI. So this is what you take. So here in this case, it's 146. So you take that number and you enter this source EUI on the P4P measure simulation tab in cell F49. So you enter that there. And then the ERP calculates the performance outcome. So this one achieved tier 3, yay, good job. And so that's all there is to it, with the exception of you need, so for program reporting, we need to be able to calculate savings. And so we do ask you to model measures. You're probably like, wait, how? I don't know, what does that mean? Well, what we mean in the case of bEQ is you essentially strip your project of measures. What do I mean by that? So you start by removing your first measure. So, and I'll show you on the next slide, but, and let's look at that now actually. Like, so let's say your as designed model had a roof with a U of 0.022. And the minimum prescriptive value was 0.032. So to remove that measure, you would run a parametric run and you would model a U value of 0.032. And so what we would get is, right, so this is just a little screenshot of the outcome from that, running those things. So when you model that higher U value, you're going to get increased energy consumption. And to get the savings, we would subtract the parametric run value from your original model. And so you basically do that process for each element of your design that exceeds the mandatory or prescriptive requirements of ASHRAE 90.1 2016. And you stack those measures on top of each other. So for the second one, we would be subtracting the as-built with the prescriptive roof. We would be subtracting your third, your second measure. So that would include, let's say you had better than code walls. So if your second parametric run was better than code walls, we would be subtracting that from the as design with the prescriptive roof. And so we could get the savings for each measure stacked on top of each other. And that allows us to understand how much of your savings are natural gas, how much are electricity, that we need to understand for program purposes. And these are outlined in detail if anyone's confused in this section of the partner guidelines, so you can check that out. And you can also download the PowerPoint to see this example here. So you repeat the process until all the measures are removed. So lastly, we'll just do a comparison of Appendix G to bEQ. So like I talked about before, no fuel switching. The next, no changing HVAC system types between the baseline and proposed. So with Appendix G, you may have you might have PTAX in the baseline, or a variable air volume, multi-zone variable air volume system with gas-fired boilers, and then your proposed is VRF. And so you've got to do a save as on your model and create a whole new one, and it might add a lot of extra work. So with bEQ, there's none of that. Your model is as your building's designed. So potentially you can save some time there. So there's no need to understand and comply with the rules for establishing the Appendix G baseline model. So that might reduce areas where you would receive review comments and areas that you'd have to address in the model and understand. So you could save a little time there. And then lastly, like we talked about, you only need to fill out the proposed design information in the ERP and compliance form. So again, that might save a little effort as well. So that's an overview of bEQ, and we would love for more partners to give it a try. Thanks.
Great, thank you, Christina. Let me see if there's any questions. All right, so as Christina was saying, hopefully some of this information was relatively new and useful. I think our goal with this particular webinar was to encourage more participation in our pre-design bonus, more participation in potentially using our bEQ compliance path versus Appendix G, in case that it might be easier, simpler for the some of the projects that we're receiving. How does the performance of the bEQ models compare to Appendix G models? Would you expect bEQ results to be the same as Appendix G for the same building? For example, if you achieve Tier 1 with Appendix G model, would you also get Tier 1 for a bEQ model? That's an interesting question. I can't say that we don't typically receive, partners don't typically submit both. Although I suspect a few of them are probably running both scenarios, at least initially, to see which one would be more favorable. I don't necessarily know if one would give significantly different results from another. Christina, I'm not sure if you know off the top of your head either. I know we run scenarios once in a while when we do testing, but
No, I'm not sure. I don't have an answer off the top of my head either, but if anyone does that analysis, we would love for you to share it with us so we can get that data to have a strong understanding of how they differ.
yeah, the most part, we almost exclusively receive Appendix G submittals. So we don't have any actual projects that we could say, oh, they explored both and either they're vastly different or relatively similar. I think there's only been one project that I can recall that explored both, and they were relatively similar. I think the obvious benefit of bEQ is you're doing less work in a sense, in not having to fill out the baseline, and even from the modeling perspective. So.
And if I can chime in, this is my
Oh yeah.
Yeah. So I think depending on the project, outcomes can be different because, for example, we know that on projects with electric resistance service water heating, or generally electricity-based service water heating or space heating, the outcome may be lower with Appendix G, but it would not be, this project would not be as effective as they follow bEQ. So I do think that for some projects, the outcomes could be even significantly different. And since both options are allowed in P4P, I think everyone is welcome to try bEQ approach, and then depending on the budget, you can then develop a Appendix baseline, and you can update model schedules if they're different from common defaults. And you would also need to use a potentially different weather file compared to what's prescribed with bEQ, and see the outcomes with both approaches. So it shouldn't be too much more work compared to just doing Appendix G from the beginning. And we were actually surprised that we didn't see more bEQ submittals because it's a simpler option. So hopefully this training will encourage more of you to try it out.
Yeah. Thank you for that. And unlike a lot of the programs that are transitioning that John was talking about, new construction and pay for performance new construction are for the moment remaining under the BPU, under the Energy Clean Energy umbrella. So we're planning for P4P new construction to continue into fiscal year 22, starting July 1. Whether there are changes to that program or that model is still very possible given the transition environment and landscape that we're in. But there's a little more runway, I guess, for this particular program to explore these options, and maybe a higher potential that we're going to continue to see these options in the near future and maybe long term. Definitely looking to promote this and see if it benefits more projects or spurs a little more participation. That was a great question. So this was the fourth of 4 trainings in our series, and hopefully most of you were able to join all of them. But if not, we did record them and place them on our website. I'm just going to show you this website really quickly in case you haven't seen it. So this is the New Jersey Clean Energy Learning Center. It's kind of a sister website to the Clean Energy Program website. There's residential and commercial resources on here, mostly trainings, learning modules, webinars. So under commercial, there's a P4P page where we have our, we have our existing and new construction new partner courses. This is kind of the P4P 101. And then further down here, you'll see the recorded trainings. Here are the 3 that we have completed and recorded over the last few months. And this one from today will also be added here in the next week or 2. So if you wanted to peruse those, or if there was someone you know on your team who wasn't able to make it and some of these topics are of interest to them, this is where you will find them. We'll also, for those of you who registered or on the call, we'll also share the slides with you in case those would be helpful as a reference instead of just a recording. So that'll be emailed out as well in the next couple of days. And I think that's all that I had. So we have just a couple minutes remaining for a lot of time, but any last call for questions or comments about any of this information? Well, if anything comes to you, you know where to reach us. You can email p4p@njcleanenergy.com or myself, and we'll be happy to answer any questions. I'd like to give a big thank you to Christina and John for presenting today and fielding questions and so forth. So that's all I have, and I guess we will wrap up, and everyone enjoy the rest of your day and this beautiful weather. Thank you.
Thanks, everyone. Thanks, Val. Thanks, John.